Hi, I'm Anthony Miller. I'm a principal engineer at Apollo GraphQL and the lead maintainer of the Apollo iOS client. So today, all of the examples I give are going to be using the language Swift that we use for Apollo iOS, but this should be principles that are applicable to building a GraphQL client in any language at all. So today, we're going to be talking about consuming GraphQL in TypeSafe languages. We're going to be doing a bunch of examples here, and so we have an example schema we're going to use for these examples today. This is for like an imaginary merchandise site for a band. I'm thinking about starting a band that performs songs about GraphQL, and I'm trying to use this for that. So I'm trying to come up with a name for my band, and I haven't come up with a great one yet. I was thinking about like Type System of a Down or Panic at the Edge node. But if you guys have better ideas, please let me know afterwards. OK, so a GraphQL schema is already strongly typed. We've got a great type system in GraphQL. So we've got scalars, enums, we have object types, there's polymorphism through both interfaces and unions, and strong nullability annotations. So why am I giving a talk on the challenges of consuming GraphQL in type-safe languages if GraphQL itself is already really, really type-safe? Well, let's look at how we represent the GraphQL data. First, we have our schema types, right? Those are defined by your GraphQL server, and they have all of your type information. You've got this exhaustive list of fields. All of the values are strongly typed, and they have nullability annotations. And then you have your selection sets, which are defined by the client that's consuming this GraphQL data. Now, this doesn't really have all of the type data on it. It has to infer it. You don't know when you're looking at this fragment here that the ID and price field and available sizes, what their nullability is, what types they have. Further, when you take this and you make a query and you get a response back, you lose even more of the type safety. So here we have a query that's fetching a list of products. It gets their ID and their price. If the product conforms or is of the t-shirt type, we get the available sizes. And if it's of the record type, we get the title of the record. And then you'll see here in our JSON response we get back when we fetch this query, we have all of this data with very, very little knowledge of what it is. The client developer has to reference back to both the query operation and to the schema. So we see that the ID field is a number, the price is a number, but one of them is an integer, one of them is a float. We see that we have this available sizes field that looks like a list of strings in our response, but actually those have to be converted into enum values of a specific type of enum. And then we have this available sizes field on one object and the title field on the other. Well, why is that? We don't know from looking at the JSON response. We have to go back and look at the query to understand, oh, this one has available sizes because it must be of this t-shirt type. This other one has a title field because it's of this vinyl record type. You have all of these things you have to reference back to on the client when you're doing this. So we have a bunch of overhead that the client developer has to understand and think about to understand what their data is when you're making it type safe. So how do we do this? Well, the best thing we've come up with after a lot of years of thinking about this is just to generate type safe models for your language. And then we map all of this data and parse and validate it onto those type safe models, right? So we're going to talk about some of the problems that come up when you decide to do that and how we design a code generation engine that is going to express all the type safety of your GraphQL data as well as we possibly can. So, OK, I will just. There we go. OK. So when you are designing generated models, there are two ways you could do this. And the first one you might think is to generate models that reflect your schema types. The schema is, after all, where all of the typed information really comes from. Here we have these models that would represent individual entity types. So you have a t-shirt type in your schema, and you have under here a t-shirt structure that is a generated model. This means that you have one model for many different operations. If you have 10 different operations in your application that are all going to be fetching data that ends up being of this t-shirt type, all of those operations are going to use the same model. And the problem with that is not every operation is going to select every single field on this schema type. So we don't know what data we're going to have, and now our model has to have all of these fields be optional, right? But that means we're not expressing the nullability of our schema anymore. We have fields that are optional and non-optional on our actual schema type, and we can't see which fields are nullable in the schema based on our generated models. So this isn't really great. It makes it really hard for developers to reason about their code, and you're going to have to go back and look at your generated, at your GraphQL schema types in order to even understand how to consume these models. And then you're going to wonder why certain fields might be nil. Is it because they weren't selected by the query that gave you this model back, or are they nil because they're actually nullable and you got a null value in your response? You don't really know all of those things when looking at and consuming this generated model. So now you're having to go back and backtrace through a bunch of code and other GraphQL data in order to get there. So we can do a much better job than this. So we decide to instead represent our GraphQL types based on the selection sets you define on your client. So here we have a fragment, and then we have a generated model for that fragment. This way you have one model per selection set. And yes, if you're fetching the same fields in different queries, you're going to have some repeated fields and repeated model objects. But now you have things that cleanly reflect your nullability and all of the data you know you're going to have. The related products field is optional here because related products on your schema is optional. You don't even have to go back and look at your schema to know that. The other fields are not optional. You see everything you're going to have and how it's going to work. So this is a better way of handling this. And this seems obvious when I explain it here, but this is honestly one of the most common questions we get is why don't we generate models that are based on our schema types? Actually, one of my coworkers, Martin, is writing a blog post that's going to be published shortly about that subject. So this is a really common question we get. I'm going to stop using this because it's not working well. So the next problem we have here is working with polymorphism. So in GraphQL, we have polymorphic types, and we deal with those in our GraphQL definitions by making what we call type cases at Apollo. I know Relay calls them type refinements, but those are just inline fragments on another type within your selection set, right? So here we have these two on t-shirt and on record, like I said before. These are going to select additional fields based on other concrete or abstract types. And the return data you're going to get from your query is dependent on the actual concrete type that is returned by your server, that the client would never know what that's going to be when they define this operation or when they fetch it, right, until they get data back from a server. So how do we represent this in our generated models? Here we have a fragment and its generated model, very, very simple here. Let's add a type case to it. So we add a type case on vinyl record here to fetch the title field if our type is a record. So to represent that, well, we could do this, right? But this isn't great because if the product isn't a record, the title field's not going to exist. So that means that we have to make the title field optional again. Same problem we have with the schema types. It's now unclear if this is optional because the title field in your schema is optional, or if it's going to be nil because of some other reason, like not the type that you got back in this fragment being a product that isn't of the vinyl record type. Now your developer has to go and look at the operation definition to see that this is part of a type case. And furthermore, even then, they have to look at the schema type, which you can see the title field is not nullable in your schema type. So you have to have all of this information you're synthesizing in order to understand how you're consuming your GraphQL data. This doesn't really reflect the type safety as well as we want it to. So what we've done instead is we've represented our abstract type cases as nested structures. That means you have concrete structs for each of your abstract types, and we have an optional type case accessor property for this. So here we have the asVinylRecord optional field, and then an asVinylRecord structure nested inside of our fragment that has that title field. Now, if you're consuming this, you see that the optionality has been hoisted up to the asVinylRecord type. If that is nil, you know that you don't have access to the title field. You can't even call that field because you don't get an asVinylRecord object back. And you understand where the nullability happened. It happened at the check on converting to this type. And if you do have the asVinylRecord, now you know that you're that type and you're guaranteed to have that title field. It's not a nullable field. You can access it. So you have a better understanding of why something is null, and you have an understanding of how you're consuming your data based on what your type system and your schema actually looks like. Now, the way we implement this is we actually take the type name field and compare that to the types in your schema when you try to call that asVinylRecord field. So this means that our client actually has to take the type name field and add it to every single one of your entities and selection sets and all of your GraphQL queries. And then we need to keep track of all of the concrete types and all of the interfaces that are implemented by those types so we can figure out when we get the type name back if the type can be converted into the type of your asVinylRecord in this case, right? That actually does have some problems, and I gave a talk about this 2 years ago at GraphQL Summit, when your schema changes after you've generated your models and compiled everything and shipped out into production. If a type that didn't implement an interface now all of a sudden does because your schema's been updated, our client's not going to know about that, and you're still going to not be able to get that conversion, even though the data would have now been sent to you by the server, because your type does conform to that interface. This is a problem that we really don't have a great solution for yet, but like I said, I gave a talk about this 2 years ago that kind of goes into some of the workarounds and things you can do to handle that one. OK, let's move on to the next concept here. So this is called field merging. What field merging is a feature in our generated models that allow us to just make them easier to use. So here we've got our schema, and we've added to it a new interface called clothing with a fabric color field. And we've made the t-shirt type, which implemented product before, also implement this clothing interface. And we have a query that's fetching a list of products, their ID and price. If the type conforms to the clothing interface, we fetch fabric color. And further, if that piece of clothing is a t-shirt, then we fetch the available sizes, right? Well, this is going to generate a model that looks like this. We've got all of these types generated right inside of each other. You can access the as clothing, and if it is convertible to clothing, you have the fabric color. If it from there is convertible to t-shirt, you have the available sizes. This works great, but these are really, really hard to consume. Imagine you were trying to use this model in a component that renders a piece of clothing, right? You would check for the as clothing field, and if it was nil, you wouldn't want to render that component. If it wasn't nil, you would. Well, you'd pass that as clothing view model or generated model to your view, and now you only have access to the fabric color field. The ID and price fields that you maybe need to render this aren't accessible to you anymore. So to solve this, you have to do a couple of weird things. You can pass both objects, the all product and its child clothing object, into your view model. But then you're having to retain multiple different objects. You end up writing a lot of weird, uncomfortable code all the time for that. The other way would be just to pass the all products into your view model and then have it check for being clothing inside of there. But really, by that time, you expect that it's there. And if it wasn't, then you're rendering a nil component or doing some error handling. And now you have to do a bunch of additional code that really shouldn't be necessary. So what we ended up seeing people doing here was taking our generated models and wrapping them in their own manually created view models that they could map all of the data and fields from our models onto their view model that they use in their view component. That solves the problem, I guess, but why are we generating models based on all the type information we have, then you're manually writing your own model and mapping all the data from one to the other? If you're manually writing models, like we've wasted our time in generating them in the first place, and we've added a bunch of code to your compiled binary size of your product, right? So this is not great. So what we've done is we've implemented this concept of field merging. And what we do here is we take all of the fields that we know to exist within a type case and just merge them down. So the as clothing now has the ID and price merged from its parent, and the as t-shirt has the ID and price merged from the all products, and the fabric color merged from as clothing. Now, whatever scope you're at, that model is nice and easy to use. What we're effectively doing here is we are looking at, when we are generating code, each of the different type cases you have, understanding what fields would exist if that type case were to be fulfilled, no matter where those fields are coming from, and generating a model that has all of that information for you. So this makes it really easy to use as your view models. Now, this is like the most simple example of field merging that exists, but this can get very, very complicated very quickly. Here, we're just like merging fields down from their parent into their children. But let's make it a little bit more complicated here. What if that t-shirt type case was a sibling of onClothing instead of nested inside of it? Here, we would do the same similar thing. Here, we'd have both of the type case successors in the parent all products object. But you notice here that the as t-shirt object is not just merging in the ID and price from its parent. It's also merging in that fabric color field from the as clothing structure. How is that happening? Well, even though this is not merging from the parent, the type system expresses the data we need for the code generation engine to understand, since the t-shirt type implements the clothing interface. Anytime we get back a type that is a t-shirt that can be converted to this as t-shirt model, we know that the clothing type case was also selected and executed. We know that that fabric color field is going to be there. So what we're doing is we're generating models that, by looking at all of the nested type cases and understanding what fields will exist if this type case is fulfilled. And that gets way, way more complicated than I have time to show today when you start having nested type cases on different interfaces that implement other interfaces, and nested entities within those that you're fetching other type cases on. It gets really, really, really complicated. I could probably write like an entire book on all of the edge cases we've resolved just working on this feature, but no one would want to read it. I really can't imagine anyone reading it. OK, we're going to move on to the last piece of the puzzle here for us today. So fragment conversion. It's really, really common for developers to define these fragments that you can use for two reasons. One, just to reuse a selection set across multiple different queries in your GraphQL, so you're following dry, you're not repeating yourself. But also, it allows us to generate models that are decoupled from the query operation that was actually fetching them. So now you can consume these generated models in your view layer or your business logic layer with a decoupling and invert your dependency from your actual networking layer. You don't have to know what query you're using to fetch this. So we still have to define a query that fetches that fragment, right? And then we generate that query itself. So we have a clothing list query here that has its data structure. That data structure is the thing that you will get returned as the response whenever you execute this clothing list query. And that has its all products field. And then you'll see that we have the products have an as clothing type case that then has the fragment conversion to the clothing details fragment inside of it. Now, we don't have an on clothing type case or inline fragment here in our query. So why do we have an as clothing there? If you see the fragment itself is being fetched on the clothing type and all products is of type product, any time that the product isn't a type that conforms to the clothing interface, that fragment's not going to be executed. Effectively, the way that the server will actually execute this operation is like this, right? You're going to have that. You just don't have to write it. And that's a convenience of GraphQL. But when we generate our models for conversion, we generate them with that type case because, again, the other way to do it would be to make the clothing details fragment converter optional. And that's not clear. That's not going to show why this is nil when it's nil. We want to understand that this is nil because it doesn't convert to clothing, not because the fragment wasn't executed. Does that make sense? And then this also can use field merging. So just like we merged fields before, we can actually merge the fields from the fragment into this query model. So now you can access the fragment if you want to use that decoupled generated model. But also, if you just want to use the model that you got back from your query and consume those fields right here, that's nice and easy to do as well. That's really useful when you have like a query that's fetching 5 or 6 different fragments. Now you have all of those built into one place, and you can access all of that merged information in one spot. You'll notice that we have this as t-shirt accessor for the on t-shirt inline fragment up there. And that actually doesn't generate a new as t-shirt object in the query. We are pointing to the as t-shirt object inside of that clothing details fragment. The code generation engine just can recognize that this is going to be exactly the same object. We don't need to generate it again. Just point to the object we already have. Now, as soon as our query ends up adding its own fragment on t-shirt and fetching different fields that were not in the fragment, now we have to actually generate in the query its own as t-shirt object that has merged in the fields from the fragment and from the query itself. I'm not going to show you what that generated code looks like, but I'm sure you can imagine it. It just literally wouldn't fit on my slides. So, OK. So those are kind of the core concepts we wanted to make sure that our generated models handled in order to consume this GraphQL data in a really type-safe way, have all of the intentionality of the nullability and the types in the way that you consume this. Now when you're consuming your GraphQL data, you never have to go and look back at the schema types. You never have to go and look back at your operations unless you want to change them and add new data to your generated models. You have all of the context of how to consume these models and why they're doing what they're doing right inside of them. But we haven't talked about how we implement this yet. So far, all of the examples I've shown you have just been like the public API of how you would consume these things, but none of the implementation of them. So when we implement these generated models, we need to think about quite a few things here. First, we want to talk about memory. So we want to make sure that we're allocating as little memory as possible because people are querying a list of products. There could be hundreds of those all in memory at the same time. You want to make sure you're using as little memory as possible. And then we want to think about how quick we can initialize these, how quickly we can access the properties on them, and how quickly we can convert them between the different type cases and do those fragment conversions. On top of that, like I said, we want to make sure that we're keeping all the type safety and nullability really clear and easy to consume. And this is where it gets a little bit tricky. When you have those type cases and fragment conversions happening, because we've implemented this field merging feature, you end up with the same fields representing the same data on multiple models. So here we have the ID and the price field on both the product and the as clothing object. And those are going to be the same exact values from the same response object, just passed from one value to the other. So if these are stored properties, when you create the asClothing object, you're copying values in memory, and you are having to map each one of those over. If you have hundreds or thousands of these and maybe 20 or 50 fields on objects, this becomes a lot of memory that's being copied around. It makes it take longer to actually access these things, and it also is duplicating them in memory at runtime. So this is not great for performance. So if that makes you think that we want to use some sort of like storage reference type box to store the values and then point to those inside of our generated models, you're on the right track. But remember, these are data models, so they really should have value semantics, not reference semantics. So how do we implement all of this? The solution we came up with was a type we call data dict. If you're building this in another language, you can call it whatever you want. But the way that this works is that data dict is really just a type that wraps a dictionary storage. So the dictionary is all of the response data that has been mapped onto this entity, and we store it for each generated model. Now, each of the entities is going to have its own data dictionary, so you'll see that like the related products will have its own data dictionary for each of those product objects, but the product struct and the asClothing struct are going to share the same data dictionary. In fact, you see this asClothing conversion, the type case converter, is going to look at, in this isClothing method, the type name of the actual response object inside of your data dict and see if it converts properly. If it does, it's going to initialize the asClothing object, not mapping every single field over, just passing that data dictionary from one object to the other. So you can make these conversions very quickly. You can pass the data around. It's not being copied in memory. You're not having to remap every single field. Super, super quick to use. And then both of these objects are going to use the same data. Then all of your property accessors are just going to be accessing data in that dictionary that is being stored, right? So all of these are just looking for data from a single key in your data dictionary. And the data dict itself, that object, has force unwrapping conversions of the data from the unsafely typed dictionary to the correct type of each of your fields as you're accessing them. And we can just force cast this and do a quick unsafe bit cast because we've already parsed and validated the data from our client, and you're consuming this data from a spec-compliant GraphQL server. So you can already make the assumption that if you're getting data back and you don't get any GraphQL errors and we've parsed and validated it already client side, it's safe to just force cast this, right? So this allows us to very, very quickly access the data we have and not ever have to repeat any data in memory. Additionally, the data dict itself, which is that reference storage box I was talking about, implements copy on write semantics so that we copy it around as a reference when we are moving from one object to another. But the minute you mutate that data, it makes a new copy, or we don't copy it as we are passing it around. Excuse me, we pass it around as a reference, and the minute you mutate it, then we make a copy of it. So your actual generated models on the public API still have value semantics. So that's how we implemented this in Swift, very similar to the way that we've done it in the Apollo Kotlin client. And I imagine any other client you wanted to build would work pretty similarly. So we'll summarize really quick here. And I actually went through this way faster than I thought I would, so I have time for questions afterwards if anyone has any. But we've explored some of the design decisions that we made while we were building the iOS client in Swift. And if you're consuming GraphQL in another language, the design might vary to take advantage of the features of your language, but the design principles are going to remain the same. So those principles are, 1, we use generated models that are based on selection sets to represent the type information of our GraphQL data. 2, we scope access to fields on type cases to clearly express the conditions in which fields are or are not selected. 3, we calculate and generate merged fields to make the models easier to work with. And 4th, we use data structures custom data structures that store the data in a way that allows it to be reused without copying it. And by doing these 4 things, we're able to consume GraphQL data with all of the safety and the expressivity that the GraphQL type system provides. So yeah, thank you all. Yeah, right here.
Thanks for the talk. I am a web developer, so I've just been thinking about why we don't have the same kind of like weird semantics when we build using TypeScript, when we generate TypeScript code versus Swift or Kotlin.
That is a great question. The best answer I have for you is that Apollo we've spent a lot of time learning and iterating on our TypeSafe models over many, many years. And our web client does not generate our own models. If you're using Apollo Web Client, we recommend that you use generated models from the GraphQL CodeGen website, which we don't own, and I can't speak to the quality of those models. But generally, the consensus or the sentiment has been, maybe not consensus, that not everyone who is doing Apollo client on web are even using TypeScript. So they might not even need the models for that reason. And B, a lot of times you just don't need the generated models. In compiled languages, it's a lot different, and it's a lot harder to deal with data that aren't put into generated model structures. Whereas in TypeScript and JavaScript, you have all of they're POJOs, and you can just access fields on your objects, and they'll be treated like fields when they're really just keys in a POJO, right? So there's not as much of a necessity for generated code. But I think that if somebody wanted to do this the right way, they would build a GraphQL TypeScript code generator that used these principles.
Thank you.
Yeah. Any other questions? OK, I got one here, and then I'll come back there.
Firstly, really great talk.
Thank you.
I have a question about the field merging. So you mentioned, and you can see in the simple example, you get a decent amount of duplication on these structs of the actual fields. And at runtime, you can manage this by just sharing the memory. Do you find in practice that this bloats your binary size?
Totally.
Or is it negligible enough, or it depends on app size?
So I can definitely talk about that. So we implemented this field merging as a really important feature because we kept getting people asking us, how can I define my operations in a better way? What are the best practices to make better generated models? And we spent a long time being like, I don't understand what you're asking. You have to fetch the data you want to fetch. If you need to show a field, you put it in your selection set. I don't understand. And what we learned over time was that the problem was what I explained about those view models. And it wasn't that they needed to define their operations differently. It's that they needed to wield the generated models differently. So we implement field merging. And now all the feedback we're getting is, oh my God, my models are huge. They're hundreds of thousands of lines of code I don't need. Can we disable this? So what we've just done recently is we have implemented a feature that allows you to set it up so that field merging can be disabled completely, it can be enabled completely, or you can only enable things from parents down to their children, or you can only merge things from fragments into queries. But then the next step for that is actually allowing you to selectively merge things in. So you may not need to merge the fields from all of your fragments into the queries, because your architecture may be that you put a bunch of fragments together, you create queries that fetch all those fragments, and then before you pass that into your business logic or into your view controllers, you are going to convert it into the fragment models. So all those fields that are merged into your queries are just a waste. But other people may actually want those, right? So we want to make it so that you can selectively do that. And at the same time, you may want to, if a fragment that you are using as your view model is referencing other fragments, you do want those fields merged in. So by using, we haven't designed the API for this yet, but I imagine we'll probably do something with a custom directive that you put on individual selection sets that can say, do field merging true or false, right? So that you can have that selective ability to generate the models the way that you want them to be and save on that binary size.
Gotcha. Makes sense. Thank you.
Thanks. OK, one more question back there. Cool. And then, yeah, we have some time. Thanks.
Another TypeScript developer.
Great, my favorite.
Would it? So I don't remember a lot of C from the little bit I had, but so
this is Swift, but yeah, that's OK.
I just remember structs. But so would a discriminating union pattern work for this, where you?
Yes, I think it would. I'm not an expert in TypeScript, but I do remember about a year ago I was playing with some TypeScript stuff, and I discovered the unions in TypeScript. And I immediately was like, oh my gosh, I wish we had this in Swift. It would have made our generated models so much better and so much easier to use. Okay. So I do think that is just a language feature that we don't have in Swift that makes it harder to do this. Because then you'd be able to, because TypeScript, everything is just that POJO, you don't need the data dict that we have, which functions as that POJO. You are just taking that POJO and checking if it can be cast to any of the types in your union, right? So functionally, what they're doing is the same as what we're doing with the data dictionary object under the hood.
Awesome. Thanks.
Cool. Thank you. Any other questions? Okay. Oh yeah, go ahead.
Do you do field merging for if I have a named fragment spread, or is it just for the inline fragment spreads?
Yep, we do it for both. Yep, we do it for both. And like I said, we're going to make it soon so that you can choose if you want it to be just for named fragments or for all things or even selectively for individuals.
I guess a follow-up, do you generate these as a centralized library, or is it co-located with the actual?
Great question. Yeah. So in Apollo version 1.0, we implemented multi-module support. So there are multiple configurations. You can have this set up so that all of your generated models are in one module that you import into your application and consume, or you can set it up so that they are embedded into like your mono target if you have a single target, or you can co-locate them into individual models or modules, and then we just have to generate a small schema metadata module that includes all that information about the types and what implemented interfaces they have that we can reference back to. But all of those options are available.
So if you're in the module, how do you know what fragments are spreading you?
If you're in,
because the spread that you have of like if on T-shirt was its own fragment in a totally separate module. Yeah, the
yeah, we'll do this.
clothing details.
Right.
How do we add the fields from as clothing or
I
into
see.
clothing details
So
fragment?
you run code generation over everything all at once. We do not have support right now, and that is the reason why it's really, really hard to do that, where you can like run code generation for individual models or modules. You run code gen over everything all at once. We generate all of the code into its different separate modules for you.
Yeah, that makes sense.
Cool. Any other questions? Okay. Well, thank you all. Have a good day.